So in this video, we're going to look at the concepts of linear dependence and independence for vectors. And this video is going to be in the playlist on vectors and matrices. And as with all the videos in that playlist, the spirit of it is going to be it's a maths video rather than a pure maths video. So what do I mean by that? Well, I mean that the vectors we're going to look at are just going to be real vectors, finite dimensional real vectors as well. So from some finite dimensional real vector space. So the entries in the vector are all going to be real numbers and there's going to be a finite number of them. So we're not going to consider the more complicated cases that you would think about in pure maths, where you might be thinking about infinite dimensional vector spaces or vector spaces over some more abstract general field. We're just going to stick to the simple, well-known, very useful, very powerful case of finite dimensional real vector spaces. And of course, this is really a very powerful part of linear algebra, these vector spaces, because the two-dimensional and three-dimensional and indeed one-dimensional case are what we use all the time in physics to model the real universe around us, either in 1, 2 or 3 dimensions. So I'm going to start by writing down quite formally what it means for vectors to be linearly dependent or linearly independent. And then what we'll do is we'll have a look at what this means more intuitively, and we'll use a geometrical picture for the three-dimensional case. So we'll look at vectors in R3 and see what this means geometrically. So initially, however, we're going to be dealing with vectors that are in some general finite dimensional real vector space Rn, and what does it mean for them to be linearly dependent or linearly independent. So we need a collection of vectors then, which we'll call v1, v2, and it goes up to some general vm. So we have this finite collection of vectors in this finite dimensional real vector space. What does it mean for this collection of vectors to be linearly dependent or linearly independent? We'll start actually with linearly independent. So we can abbreviate that to Li for short. So if all of the vectors in this set are linearly independent, it means that if you have some linear combination of them, so C1 times V1 plus C2 times V2 plus all the way up to Cm times Vm, where all of these coefficients, the Ci's, they're just scalars, real numbers. So this is a linear combination of these n vectors. You're taking some multiple of this one, then adding it to some multiple of this one, and then adding all of these together. So all of these linear multiples of the vectors you're adding together. So overall, that's a linear combination of those n vectors. If they are linearly independent, then it means that if you have a linear combination of them that overall makes the zero vector, so this here is representing the zero vector, so the vector with zeros in all n entries, then the only linear combination that does that is the trivial one, where all the Ci's are 0. So if you put 0 in front of all the vectors, then of course 0 times any vector makes the 0 vector, so this becomes the 0 vector, this one also becomes the 0 vector, all of them turn to the 0 vector, and then you're just adding up m copies of the 0 vector, which makes the 0 vector. So that is a linear combination that always can be guaranteed to make the 0 vector. If they are linearly independent, it means that that is the only linear combination that you can use to make the 0 vector. There is no other one where some of these coefficients aren't 0 that makes the 0 vector. So that's the definition of linear independence in full formality. And indeed, that carries over into the more abstract case of vector spaces over any general field that are finite dimensional. Now, let's have a look at what it means for them to be linearly dependent. So it's the opposite of that. So if they are linearly dependent, it means that you have some other linear combination that does make the 0 vector. So some non-trivial linear combination. So I'll write it out again. So C1 V1 plus C2 V2 plus all the way up to Cm Vm makes the 0 vector. And this time, this is a non-trivial. So we have some non-trivial linear combinations, so at least some of these are non-zero in front of here. Not all of them are necessarily non-zero. Some of them you might not need. So for instance, V1, we might need no contribution from v1, so you might still have a 0 here, but some of the other ones are guaranteed to be non-zero. That's what a non-trivial linear combination of the vectors means, not this linear combination where all the coefficients are 0. This is the trivial linear combination that makes the 0 vector. So if for your set of vectors there is a non-trivial linear combination that makes the 0 vector, then your set of vectors is said to be linearly dependent. If there is no such non-trivial linear combination that makes the 0 vector, and the only linear combination that does make the 0 vector is this trivial one, then you say that your collection of vectors is linearly independent. Now, let's explore this a little bit further. Firstly, in the general case of Rn vectors, and then we'll explore it even better with the example of R3, and we can see how it has geometrical meaning. If they are linearly dependent, then we have some non-trivial linear combination that gives the 0 vector. So some of these coefficients are assured to be non-zero, and without loss of generality, let's just assume that this C11 here is non-zero, so this is not equal to 0. We can do that without loss of generality, because after all, these are all just labelled up generally, so you know, one of them is guaranteed to be non-zero. In fact, more than one of them is guaranteed to be non-zero. So one of the ones that's non-zero, we might as well just relabel that up as the first one. So without loss of generality, we can assume that the first one is non-zero. So what you're then able to do is rewrite this equation as C1 times V1 is equal to minus C2 times V2 minus C3 times V3. So just taking all the rest of this onto the right-hand side here, and then it continues on, all the way down to minus Cn Vm. And now because C1 is non-zero, we're talking about the real numbers here. It's a field, so it will have a multiplicative inverse, 1 over C1. So we can divide through by C1, and we'll get that V1 is equal to minus C2 over C1 times V2 minus C3 over C1 V3, all the way down to minus Cn over C1 Vn. So these things here now, they might look complicated because they've got this minus sign and they're being divided by C1, but these things are all just real numbers. So what you've actually managed to do is write V1 here as a linear combination of the other vectors in your set. So these are just scalars. You're taking some scalar times V2, you're adding it to some scalar times V3, etc., all the way up to Vm. And again, some of these might be 0. If these coefficients here were 0 up here, then they'll still be 0 down here, so you won't need any contribution from that respective vector. But the point is, some of them will be non-zero, and therefore you've managed to write V1 as a linear combination in terms of your other ones. So that is why it's called linearly dependent, because actually this one isn't independent of the other ones. You've got it. You can write it in terms of the other ones. You can build it out of a linear combination of the other ones. So actually V1's purpose in here is kind of, it's not necessary in there. The number of things you could reach in this set, the span of your set of vectors, is not added to by having V1, because V1 is linearly dependent on the others. So that's intuitively what linear dependence means. It means that you can write one of the vectors as a linear combination of the other ones, and therefore by having it in that set, it's not independent from the other ones, it's actually within the span of the other ones, and putting it therefore into the set doesn't actually increase the span of the set of vectors. So if this is confusing to you, don't worry, I'm going to now go to a concrete example and show you what these concepts mean geometrically. So we're now going to the example of R3, and that's a beautiful thing to look at because, of course, we can think geometrically. We can think that this abstract mathematical structure is capturing the same pattern that is in the three-dimensional universe around us, so we can visualize it as the three-dimensional universe around us. So, this is the concept. Let's say we are building a set of vectors. We start off with putting one vector in this set, V1, and let's say geometrically V1 might look something like that. So actually writing this out in terms of its components, in terms of the standard basis, it might be, let's go along in the x direction 2, let's go along in the y direction 1, and let's go up in the z direction 1. So this is the z direction, this is the x direction, and then the y direction is going into the board. So this, I hope you can kind of see that we've gone along 2, we've gone into the board 1, then we've gone up 1. That's what this vector is. Now, this vector has a span. So if you haven't seen this concept of span before, span means all of the vectors that you could get to in the vector space R3 by taking linear combinations of your vectors. And because we've only got one vector, linear combinations just means all linear multiples. So consider all things of the form C1, V1, where C1 is allowed to equal any real number. So you could make it 1, of course that will keep you at the same vector. You could make it 2. If you multiply this by 2, it's going to become 4, 2, 2. And of course that geometrically has a great meaning. If you multiply it by 2, it's stretching this vector out to twice the length. So it's going to include that one. Now let's think about doing some other ones. Multiplying it by -1. Geometrically, well, firstly algebraically, that would give us the vector. Oh, and I don't want to do it in red. Red doesn't show up very well. So algebraically, and I've managed to not change my colour. So multiplying it by -1, algebraically would give -2, -1, -1. Geometrically, it flips the vector in the other direction. It's going to go down here now. So that's that vector multiplied by -1. And hopefully you can see that if we multiply this by half, it will geometrically have gone to half the length. If we multiply it by 2/3, it will be 2/3 the length. And we're multiplying it by every single real number. So we're going to get a huge, great set of vectors if we did that. So if we considered the set of all things of this form, C1, V1, where C1 is allowed to be any real number, that would be the set of the span of V1. So this is the span of the vector V1 as a set, all the vectors that you can reach from taking linear combinations of V1. And geometrically, what does that look like? Well, it's going to be the straight line that is in the three-dimensional space that's in line with this vector, because everything on that straight line you can get to by taking a multiple of this vector. You just have to stretch it out by the relevant amount. So if you want the one that's 4 times it, well, that's a bit far for 4 times, maybe here, you just multiply this by 4 times and you get there. If you wanted this point, that looks about 2.7 maybe. So you take something roughly around there to get to there. And all these negative ones in this direction, you just need to multiply it by some negative real number to get there. And if you multiply it by 0, of course, you'll get the origin. You'll get the 0 vector. So all the points on that straight line, that's going to be the span of this vector. Now, that concept of span is very important to thinking about the concept of linear dependence and linear independence. Let's say we're now going to add another vector into this set. Now, if you've only got one vector in the set, then your set of vectors is linearly independent. It's only once you've got more than one vector inside the set that it could become linearly dependent. So this set of 2 vectors is now going to be linearly dependent if it is the case that this new vector that I've stuck in is actually inside the span of V1. So let's say that I made V2 equal to 2 times V1. So this vector here. That, if I then think about what the span of my new set is, it's not increased at all, because the span of my new set would now be all linear combinations of those 2 vectors. So if I wanted the span of the set of V1 and V2, this would be the set of all things of the form C1 times V1 plus C2 times V2. That's all linear combinations. So when you have something of this form, where you have vectors with scalar multiples being added together, we call that a linear combination of the 2 vectors. So the span is the set of all linear combinations of the 2 vectors, where C1 and C2 are allowed to vary over the real line. Well, this isn't going to have grown. It's still going to be the same. It's still going to be this line, because C1, V1 can get us to any point on this line. If we think about what the span of V2 is, it's in that same line, so it's going to be the same line. You know, all multiples of it just gives this same line in 3 dimensions. So it's not going to be possible, for instance, to get here by taking a linear combination of these two because they're always in parallel there. So how on earth can you add two of them together to get something that's outside of that line? You can't, is the answer. So if you take any linear multiple of v1, it's going to be on this line. If you take any linear multiple of v2, it's going to be on this line. Adding those two linear multiples together is still going to be on that line, so you can't get off that line. So the span has not increased by putting v2 in there. This is the concept that this set is linearly dependent. Having v2 there served no purpose at all. You haven't increased your span by having v2. Because v2 was linearly dependent on v1, you could write v2 as a linear combination of your other vectors, which in this case is just v1, so you can write v2 as equal to 2 times v1. And of course, we could then find a non-trivial linear combination of v1 and v2 that makes the 0 vector. So if I, for instance, looked at negative 2 times v1 plus 2 times v2, sorry, not 2 times v2, it should just be 1 times v2, plus v2, that will give the 0 vector, because v2 is this vector, and then minus v1 is this vector, so minus 2 of that will go backwards and will give you then the 0 vector. So because this one can be written as a linear multiple of the other one, i.e. it's linearly dependent on it, that can then be rearranged into this equation to give us a non-trivial linear combination of the overall set of vectors, giving the 0 vector. So those two, I hope it's now making sense how these two definitions of linear dependence, this one in terms of finding a linear combination of the set of vectors that's non-trivial and gives the 0 vector, and this one, i.e. you can write one of the vectors as a linear combination of the others, are equivalent to one another and what that geometrically means. Now, if we want to do something more sensible, let's add in a v2 that is not linearly dependent on v1. So let's instead now make v2 this vector. So that vector might be, oh, I don't know, 1, negative 1, 0, let's say. That looks kind of geometrically convincing, as that's what that vector is. So we're going 1 along in the x direction. We're coming, oh, actually, I've made a mistake here because I need to specify which direction of the y-axis is positive. Am I thinking of this as the positive direction, i.e. coming out of the board, or am I thinking of going into the board? I'm thinking of going into the board as being the positive direction, and I was thinking that this vector here was going into the board, hence why it had a positive 1 there. It came along 2, it went up 1, and then it went into the board 1. This one is coming out of the board. It's gone along 1 in the x direction, and then it's coming out of the board, so the negative y-axis is in this direction. So this vector cannot be written as a linear multiple of this one. No linear multiple of this will give this, and you can see that because it's quite obviously not on the same straight line. So adding it into this set is going to actually increase your span. So if we now think of our set, and I could do with some more space, but I don't want to lose my picture. So our set is now this vector v1, which is still 2, 1, 1, and this vector which is v2, which is 1, negative 1, 0. If we think about the span of that now, it's going to be all linear combinations, so c1 times v1 plus c2 times v2, where c1 and c2 are allowed to vary over the real line. So what's that going to do? Let's think about this geometrically. Firstly, let's think about what all the linear multiples of v2 look like. So v2 is here. Just as before, all linear multiples of v2 is going to be a straight line. So it's going to be this straight line that's going to be, oops, I missed that completely. I've kind of ruined the picture a little bit there. So ignore that yellow line. I'm going to try and rub it out, but this is probably going to make a complete mess of the picture now. So trying to get rid of that yellow line. So trying to correct the yellow line so that it's actually in line with that vector there, that's a little bit better. So you get what I'm trying to do. This is supposed to be all linear multiples of v2. So, if you multiply it by a negative number, it'll go off in this direction. If you multiply it by 2, it'll come out maybe to here. If you multiply it by 3, it'll come out to here. If you multiply it by all of the fractions and all of the other irrational numbers that exist, you can get it to any where you want on this sort of section here. So that's going to be the line that is all linear multiples of v2. So then if we add any one of these to any one that's in the line of all linear multiples of v1, you can see that actually that's going to define a plane, and I'm not going to attempt to draw this on the picture, but actually I will do some attempts. So it's going to make a plane kind of like this, that's going to go through both of those lines. So it's kind of complicated to see how this is going to work. Hopefully your 3D visualization skills are good. So we have this line that's in the xy plane. So here is the xy plane. That doesn't have any up or down components. It's a straight line in the plane z is equal to 0. This line is then sort of inclined upwards and is going at that sort of direction. So you can sort of imagine how there's only one plane that will include both of those lines, and it's sort of angled at this sort of direction. So any of the points in our three-dimensional vector space that is on that plane, you will be able to get to by taking a linear combination of these two vectors. You just need to go along however much in this direction, and then go along however much you need in the direction of this red line here. So you'll be able to find the correct linear multiples you need of v1 and v2 to get to any point on this plane. So its span will have become a plane. So that is then the concept of a linearly independent vector. v2 could not be written as a multiple of v1, and therefore there can be no linear combination of these two vectors, non-trivial linear combination that gives the 0 vector. Because if there was a non-trivial linear combination that gave the 0 vector, we would be able to rearrange that into an equation that says that one of them is a linear multiple of the other. So imagine if we had c1 times v1 plus c2 times v2 is equal to 0, where these are not the trivial linear combination, i.e. they're not 0. So that means that both of them have to not be 0, because if one of them was equal to 0 and the other one wasn't equal to 0, then obviously that's garbage. You can't have a non-zero vector being multiplied by a non-zero scalar to give the 0 vector. So they'd have to both be non-zero. So you'd then be able to rewrite this as c1 v1 is equal to minus c2 v2, and then divide through by c1 because it's not 0. So you've got minus c2 over c1 times v2. And this is not good because this is just some real number. So you've therefore got that v1 is a linear multiple of v2, which obviously is not true. So that is the concept then of them being linearly independent, that this one is not buildable out of linear combinations of the other ones. And it means that when you add that new linearly independent one to the set, that the new span of your set of vectors, the new subspace that is built by taking linear combinations of these, is now bigger than before you added it. Now we can go one step further. We can add another vector in here. We can add a v3. And again, that's just to completely get into our heads this concept of linear dependence and independence. Let's think about the case where v3 is going to be linearly dependent on v1 and v2. And then let's think about the case where v3 is going to be linearly independent from v1 to v2. And then we'll have completed our understanding, our geometrical understanding in this three-dimensional case of what linear dependence and independence means. So firstly, let's do the linearly dependent case. So if it's going to be linearly dependent on the other two, it means that it is a linear combination of these two. And that means that it's going to be inside this plane that is defined by the span of the other two. So an example would be if and I'm running out of space, we'll have to go down here. If I made v3 equal to, let's just keep it simple, so we'll just do v1 plus v2, so let's actually work out what that is. So 2, 1, 1 plus 1 minus 1, 0. So that's going to give 3, then 0, and then 1. So all I've done is add that vector to that vector. So this gives what this vector overall is. So it's on the picture, it's what we've done is we've taken v1 here, and then we've added on v2, which is here. So we've ended up kind of here with that vector, and you can see that that has no y component, so we've just gone along 3 and then we've gone up 1 in the z direction. doesn't quite look perfect on the picture, but you hopefully get the idea that that's the vector we've ended up with as v3. So I'll mark that on in green here. So that is the vector v3, and I'll go over it in green. So v3 in this case is going to be linearly dependent on the other two, meaning that it's built out of a linear combination of the other two, and you can see that adding it in there is not going to increase the span of this set of vectors. If you now look at all linear combinations of these three, so if we think about the span now as the set of C1, V1, plus C2, V2, plus C3, V3, where C1, C2, and C3 are all real numbers and can range over whatever real number you like, that is actually still going to be the plane, because from this bit we can get to anywhere on that yellow plane. And then if you think about what all linear multiples of v3 look like, that's a line that is actually going to be inside the plane. So adding on to any point inside this plane a linear multiple of v3 is still going to keep it in the plane, because this line is within the plane itself, so you'll just be moving your point inside the plane. So if you take any point, let's say this point here inside the plane, and you decide to add some linear multiple of v3, it's like doing that, but so you'll be moving parallel to the line of v3, parallel to v3, and moving parallel to v3 isn't going to take you out of the plane, it's going to keep you in the plane. So you're never going to get to one of these points that's outside of the plane. For instance, this point down here, 0, 0, minus 1, that's not in the plane. You're never going to be able to get to that point in this. So adding on that linearly dependent vector does not increase the span. And v3 being linearly dependent means that it can be written as a linear combination of the other two, and of course that means that there's going to be a non-trivial linear combination of the three of them that gives 0. So just taking this equation that we've got here, v3 is equal to v1 plus v2, we can write that as v1 plus v2 minus v3 is equal to 0. That's a linear combination of all three of them that's non-trivial. You've got 1 as the coefficient here, 1 as the coefficient here, minus 1 as the coefficient here, that is giving the 0 vector. So they are linearly dependent. To complete this discussion then, let's just finally consider the case where all three of them are linearly independent, and intuitively what does that mean? So we'll keep v1 and v2 the same, but now let's let v3 be linearly independent from v1 and v2, meaning that it cannot be written as a linear combination of the two, and therefore it is not something that's inside the plane, so it's some vector that's not inside the plane. And to keep things simple, we might as well use that example that I've already given you of something that's not inside the plane. So we'll have 0, 0, minus 1 as our final example for what v3 is equal to. So it would now be this vector coming down here. And if you think now about what the span of this set of three vectors that are linearly independent is going to be, so it's going to be what we've written down here, all linear combinations of the three vectors that are possible. Well, think of what all the linear multiples of v3 is going to look like. That's going to be a very simple straight line. So it's going to be the straight line that's parallel to v3, but v3 is parallel itself to the z-axis, so it's going to be the line of the z-axis. So we'll colour that in green. That's all linear multiples of v3. And now if we think about taking any linear combination of v1 and v2, and then we can now add it to any linear multiple of v3, so that means we can go to any point on this two-dimensional plane and we can add on any linear multiple of v3, so that means we can go up and down parallel to the z-axis as much as we like. So for instance, if we go up to that blue point, we can now go up and down as much as we like, which corresponds to adding on whatever linear multiple of v3 we like. So that means we can get to all of these points that are on this green line, and we can do that for every single point that's in the yellow plane. So you can see how this means that we're going to be able to get to any point in the whole of the three-dimensional space. So adding on another linearly independent vector has increased the span of the set of vectors now, and it is now equal to the entire vector space R3. So I hope that has helped to illustrate the concept of linear dependence and linear independence intuitively. Just to summarise, if you have your set of vectors now back in the general Rn, and they are linearly independent, it means that all of the vectors inside here are independent from one another. None of them can be written as linear combinations of the other ones. None of them are inside the span of the other ones. Every single one of them in this set is contributing additional span by being there, and if you were to take one of them away, it would reduce the span of your overall set. In contrast, for linear dependent vectors, it means that some of them in here aren't actually necessary. Some of them can be written as linear combinations of the other ones, and therefore they're not contributing any additional span by being there, and you could take them away and your span would still be exactly the same. So we'll end there. Thank you for watching.